On here with learning target 8b, volumes of revolution. So our first example says write but do not evaluate an integral expression that gives the volume of the solid obtained by rotating the region bounded by the curves y equals x squared and y equals 4 about the line y equals 4. So what makes this example different than stuff in our last video is we're now going to start rotating about horizontal and vertical lines that are not the x or the y axis. So I'm going to do the same thing we started last time. I'm going to start by labeling my curves. So it says I'm bounded by y equals x squared, which is this whole curve down here underneath. So if I label that, then we have this guy as y equals x squared technical difficulties. There we go, as y equals x squared, and then y equals 4 is the horizontal line up here where this is actually bounded. So this top portion of this is y equals 4. They're saying we want to rotate this region, so this entire shape inside, about the line y equals 4. So I'm actually going to rotate it about the same line that I'm bounded by. So I'm going to take this shape and I'm going to flip it up and over. If we draw that in 3 dimensions, what we're going to end up getting here is, let me move that axis down for us, since everything is going to be above the x-axis. So I have this half type circle shape, and as we rotate it up and over, I'm actually getting kind of like a football shape looking. This object is going to be completely solid since the axis of revolution here is touching the region we're rotating about. So based off of that, I want you guys to determine right now if you think this will be a disc or a washer method, and if you think we'll be stacking these up like bread or like pancakes. The first thing I know is since the axis of revolution here is bounding the curve completely, I'm going to end up getting a disc as my cross section. So the area of my disc, I will only have one radius, and it will be pi r squared. Now, when I rotate this about, because we slice perpendicular to the axis of revolution, then my cross sections here are going to be coming down, and they're going to be these solid dish shapes there. And that piece right there is actually going to be my radius that I get. This is the portion of the curve that I'm getting as I flip it over. So if I were to draw my radius in the portion that I have, it's going from my axis of revolution down to this curve. So that is another place that I could draw my radius. If I go back to the two-dimensional graph, what we're looking at right here is to get my radius, I go to my axis of revolution, which is y equals 4, and I go towards the first curve that I'm going to intersect, or in this case, the only curve, and that right there is going to be my radius. Now, because I'm slicing vertically, since I'm going perpendicular to the axis of revolution, I'm going to actually stack these up like a loaf of bread. So in this case, I'm dealing with our bread scenario that we had from last time, which means I am in terms of x's for this entire integral and for the limits of integration. So when I think about this, this is the first time we're actually seeing something that goes outside of quadrant 1. So I have this entire region, so they're stacking up all the way over from whatever this x value is on the left side, all the way over to this x value on the right side. Well, I need to figure out what those x values are. Well, they're coming based off of when I plug something in to y equals x squared and I get 4 out. Well, if I plug in 2 into x squared and I square it, I will get 4. So this is the coordinate pair there, 2, 4. Likewise, if I plug in -2 and I square it, I will also get 4. So that tells me that my bounds are stacking up from x equals -2 all the way to x equals +2. I know I have a disk since this is a solid object, so I just have one radius that I'm finding. So I need to get an equation for that. Well, I am in terms of x, so I'm going to deal with top minus bottom to get the distance here. So I want to pay attention to what is the top portion of this radius and what is the bottom portion. Well, the top portion is when it intersects the curve y equals 4. So my top value here is going to be 4 minus the bottom value I'm getting from when it intersects y equals x squared. So the bottom function is x squared. No matter where I draw a radius on here, if I have a tiny guy over here, I'm always starting at 4 since that is my top curve and going down to x squared since that is the bottom curve, regardless of where I take this cross section. From here, that tells me that I can get the area of my cross section. So the area of the cross section is going to be equal to pi r squared since we just have a disk. So in this case, I'm going to get pi times, well, my radius here doesn't simplify down all the way because I can't combine 4 and x squared, so I just get my my area of my cross section to be pi times the quantity 4 minus x squared squared. Now if I wanted to, I could FOIL this out and I could simplify it, but what I cannot do is I cannot distribute the square to each piece. We've talked about this in class before this year. It's called the freshman's dream, where I really wish I could distribute it to each piece. But remember, as a little kind of review from algebra, if I have a quantity squared, that is equal to 4 minus x squared itself times another quantity of itself. And so to simplify this out, I'd have to FOIL the whole thing out, which I could do, but there's no need to do it since we're not going to simplify free response questions. So instead of taking the time to FOIL this all the way out, I'm going to just leave it as my radius squared. Now my final answer is they want the volume of this. Well, now that I have my bounds, I have my area of my cross section. To get the volume, I'm going to integrate my area. When I do so, I have my bounds going from x equals -2 to x equals +2 of my area of my cross section, which is pi times 4 minus x squared, the entire thing squared there, and then this is with respect to x. So this entire piece right here would be our volume that we get by rotating that region about the line y equals +4. Let's look at our next example here. So this guy says to write but do not evaluate an integral expression that gives the volume of a solid generated by rotating the region bounded by the curves y equals x cubed, y equals the square root of x, and about the line x equals 1. Well, let's start by labeling our graph over here. I have two curves, y equals x cubed, and I have y equals the square root of x. Well, based off of the shapes of these graphs, I'm going from 0, 0 to 1, 1. This is not a large portion of this graph by any means, but if we kind of think about what these shapes look like, x cubed is a graph that slowly grows and then starts to kind of grow faster over time. So it's going to be the portion that's curving down and then up, so it's starting and going concave up. So this guy over here, if I label it, is going to be y equals x cubed. And if I review what the square root graph looks like, that only takes in positive values, and that actually curves over time and is actually a concave down graph. So this guy right there would be y equals the square root of x. Now they're taking this kind of petal-like shape and they're saying rotate it about the line x equals 1. Well, x equals 1 is a vertical line. It's actually the line that's going to touch this point right here and run vertically there. Let's insert a straight line for us to see this. But this vertical line coming all the way down, and let's kind of make that bolder. I'll kind of change the color so we can see what's happening here. So my axis of revolution then is this line right here, vertical line, that is x equals 1 running through the graph. And we're going to rotate it over, so we're flipping this guy over to the right this time as it rotates. Now I want you guys to take a second, pause the video, and decide if you think this is going to be a disc or a washer, and also if you think that this will be in terms of x or in terms of y for our final answer. Well, let's go ahead and draw this three-dimensional shape so that I get kind of an idea of what it looks like. So I've got my x-axis and my y-axis here. I've got x equals 1 is this line I'm rotating about, and I have this petal-like shape. So I've got a petal on this half, and as I rotate it over, I get a mirror image on the other side. And because there's axis that I'm rotating about does not completely touch the curve here, see how there's this open space right there? This is actually going to produce a washer. when it gets flipped over, which means I'm going to have two radii. I'm going to have my larger radius, which we used a capital R for, and I'm going to have my smaller radius, which we used our lowercase r for. When I think about how I'm going to stack this, well, I'm going to take a cross section. It's going perpendicular to the axis of revolution. So if I draw this cross section here, I'm getting my washer shape that I have, and it's all this region in between the two circles. Well, these are stacking up along this vertical line. So they're starting all the way down here, which is actually at y equals 0, and stacking all the way up to the top, which would be at y equals 1. This is one of those pancake scenarios, since they're stacking one on top of each other, so which tells me I should be in terms of y. So it makes sense then that my bounds are starting at y equals 0, down here at the bottom where the largest washer would be, and they're stacking all the way up to y equals 1 over time. The last thing I need to figure out is, well, what are my two radii? Well, let's go back and look at this original graph that we have. So when I draw my radii, I'm starting at the axis of revolution and I'm going towards the curve. Because this is a washer, I'm going to have two. I'm going to have one that stops at the first curve. That will be my little r. So if I go to my two-dimensional graph, I'm starting at the axis of revolution and I'm going towards that first curve. So that green curve right there is my little radius. Now I can do the same thing to get my big radius. I start at the axis of revolution and I go all the way out to the furthest curve. So on the two-dimensional graph, it means I'm starting at the axis of revolution, going past the first curve, all the way to the furthest curve out there, and that will be my capital R. Well, because we're in terms of y, I have to be thinking about this in terms of what is the right side of this curve. Hold on. Since we're in terms of y, we have to think about this as what is the right side of this curve minus what's the left side curve that we're intersecting. So let's start with our big radius here. When I think about this big radius, the right curve here is the axis of revolution. So that would be x equals 1. So my right curve there is 1. My left curve that I have is all the way over here, which was y equals the square root of x. Well, I can't plug in the square root of x because I need to be in terms of y, since my bounds are in terms of y. So instead, I need to isolate this and make this an x equals equation. To do that, I'll need to square both sides. So I end up with y squared equals x. What that tells me then is my leftmost curve is actually going to be y squared. So my big radius will be 1, my axis of revolution, minus my left curve there, which is y squared. Now we can do the same thing to find our little radius. So our little radius is starting at the axis of revolution, that would be the right side, so it's also 1 minus. Now the left curve this time is coming from y equals x cubed. Well, likewise, I can't plug in x cubed because I have to be in terms of y. So if I take this equation and I isolate it and make it x equals, I'll cube root both sides, and I get the cube root of y is equal to x. And what that tells me then is I need to plug in the cube root of y as my rightmost bound that I have on here. Now that we have both the axis of revolution, or now that we have our axis of revolution as part of our radii and I have my other two curves and I have my bounds, I can set up my final equation for volume then. So remember, volume is the integral of the area of a cross section. My area of my cross section, since it's a washer, is going to be pi times big R squared minus pi times little r squared. So I'm going to get the integral from y equals 0 to y equals 1 of pi times, well, my big radius is 1 minus y squared. And then I square that because it's big radius squared minus pi times my little radius is 1 minus the cube root of y. That is also squared. And then, of course, with respect to y from there. Now again, there's no need to go through the time to set this up as 1 minus y squared times itself again and FOIL everything out, because I don't need to combine anything on a free response question. So this setup right here will be my final answer to my volume. Okay, let's scroll down and check our next example. I want you guys to pause the video right now and take the time to draw this out with where the axis of revolution is, and to figure out if you think it's going to be a disc or a washer, and if we're going to set this up as like a bread, so in terms of X, or if it's going to be a pancake in terms of Y. Let's read question 7. It says, write but do not evaluate an integral expression that gives the volume of a solid generated by rotating the region bounded by the curves y equals x and y equals the square root of x about the line x equals 2. Well, let's start by labeling this. The first curve they gave us was y equals x. That's actually the straight line down here. And y equals the square root of x is the curve piece that isn't going on top. They're asking us to rotate this about the line x equals 2. Well, x equals 2 is a vertical line, and if I look at this, this is stopping this graph at 1. I'm rotating about something that is way over here at 2. So if I insert my axis of revolution right now, I'm going to have a curve, or I'm going to have an axis that is actually not touching at all the region I'm rotating about. So if I insert that axis of revolution right there, change the color so we can see a little bit better. Now we're rotating about this x equals 2 line, and if I look at it, the region I'm taking is not touching this at all, which means when I flip this over, if I try to sketch out what a three-dimensional graph is going to look like here, stopping at 1, I have this rotation line at x equals 2. Well, my graph, when I flip it over, I'm going to get a mirror image. And since there's a unit distance here between 1 and 2, that means this graph is not going to start up again until 3, and it's going to actually finish at 4. And I'll have this straight line and that curve on top. Now when I rotate this and I flip this around and I get this three-dimensional shape here, this is going to create some donut-like feature because I'll have a hole going down the center of it. This is definitely going to be a washer scenario because the axis of revolution isn't even touching the region I'm rotating about. So we'll be trying to find our big radius, and we'll also be trying to find our little radius. Now if I try to think about if I'm in terms of x or y, let's look at what a cross-section of this graph looks like. So if I draw a cross-section on here, I slice perpendicular, so I have a horizontal cross-section that's got this gigantic kind of inner circle here, and then this slightly larger outer circle if we were to draw it. So it goes all the way around there. So this is, as I stack them, I'm going from the bottom portion down here, which is actually going from y equals 0 all the way up to where they intersected, which was at y equals 1. So this will be in terms of pancakes, like the last example was, since I'm stacking them up vertically. The next step I have to find is, well, what are my radii? Well, let's start with our little radius. So my radii always start at the axis of revolution, so they're starting at x equals 2 and they go towards the curves. So there's my first one. If I draw it on my two-dimensional graph, I go from my axis of revolution, then I go out to the first curve I hit. There in green is my little radius. To do my big radius, I go back to the axis of revolution and I go all the way out to the outer curve. So on the two-dimensional graph, from the axis of revolution all the way out to my outer curve will be my bigger radius. I want you guys to take a moment right now, pause the video, and write out what your two equations are for your big radius and for your small radius. Let's check those. So if I start with my big radius here that I have, oops, the pen's delaying itself. I start with my big capital R there that I have. I am in terms of y because my bounds were in terms of y, which means I'm thinking about this as right curve minus left curve. Well, my right curve here is x equals 2, So that's my axis of revolution, minus the left curve here is coming from y equals the square root of x. Now I can't plug in the square root of x because I need to plug in a y value. So if I take this and I square both sides, we get y squared equals x, and that tells me that my leftmost curve is going to be y squared. Now let's do the same thing to find our little radius. So our little radius also has a right side of 2, minus the left curve here is coming from y equals x. Well, in this case, I have x already isolated, so I can just substitute in the y value there. Now that we have all of our pieces to set up our volume, let's go ahead and put them together. So the volume is going to be equal to the integral as y goes from 0 to 1 of pi times my big radius squared, which is 2 minus y squared, minus pi times my little radius squared, which is 2 minus y, and then square that with respect to y there. And this right here will be our final answer for example 7. Okay, let's scroll down and look at example 8 now. So why don't you guys pause the video again and decide, is this going to be a disc or a washer? And if you're going to be in terms of x or in terms of y. So example 8 says, write but do not evaluate an integral expression that gives the volume of a solid generated by rotating the region bounded by the curve y equals sine of x, so we have a trig function now, and y equals 0, with x being bounded in between 0 and pi, and we're going about the line y equals -2. Well, let's draw this out because there's a lot going on. So y equals sine of x, remember, if I draw one cycle of it, curves up and over all the way. But I'm bounded between 0 and pi, so I'm actually just looking at the first portion of this graph here, which is this upside down U shape, since I'm stopping at pi there. I'm also bounded by y equals 0, which is this line down below. So I'm going to label that as y equals 0, and the top curve as y equals sine of x. They want me to rotate about the line y equals -2. Well, I've got to add that to my graph then, because that's going to be way down here. So let's say -1 is there. I'm going to put -2 down here. Oop. Silly pen. So if I keep drawing my axis, I've got this horizontal line down here that we are rotating about, and it is flipping over from there, and we're taking this whole kind of half circle region and flipping it around. Well, if I try to draw to the best of my abilities a three-dimensional graph, I've got my axis here at -2 that I'm flipping over, which means I have a distance of 2 between them, so -4 is going to be the first place where I get the other half of this graph as it flips around, and it's definitely creating a nice pretty donut shape here as this guy rotates about that graph. Well, when I think about my cross-section, I must slice perpendicular to the axis of revolution, which means my cross-sections are going to go vertical. So I'm going to have this inner radius right here, then my outer radius as it keeps going to there. Now when I think about stacking these up, I'm starting over here and starting at x equals 0 all the way over to, in this case, x equals pi, since that was my largest value on the x-axis, and this is stacking up like a loaf of bread, which is going along with the fact that I am in terms of x. So my bounds are going from x equals 0 on the left side, stacking all the washers up till I get to x equals pi. The other thing we've also decided on is that it is a washer, so let's write out that general area then. So we will be after trying to find 2 radii on this. Well, let's start with our inner radius. So on all of these, we've always started to find our radius by starting at the axis of revolution, which means I'm going to start down here actually at y equals -2 and go towards my shape. So as I go up towards my graph, the first line I intersect is y equals 0. So there's my little radius. Now my big radius starts also at the axis of revolution and goes all the way up past the first curve, and it stops at the second curve. That right there will be my big radius. Why don't you guys pause the video right now and decide what those two equations are for your big radius and your little radius. Okay, let's check our big radius. So our big radius, because I'm in terms of x now, I'm thinking top curve minus bottom curve, because I have a top portion of this line and a bottom portion. So my top portion of this line is intersecting y equals sine of x, and this is exactly how I need it since I want to be in terms of x anyway. So my top portion of this graph is sine of x minus, now the bottom curve I'm intersecting is the axis of revolution, which is -2. So sine of x minus a -2, or we can write that as sine of x plus 2. And we're going to do the same thing for our little radius. So if I look at my little radius, oops. If I go back and I look at my little radius that we have, this is starting up at the line y equals 0, so the top portion of this is actually just 0, minus the bottom curve here is the axis of revolution, so I end up with my little radius being +2. And that should make some sense here, because no matter where I draw this little radius, it's always a fixed distance of 2 units. Now that I have my 2 radii and I have my bounds, I can set up my equation for volume. So volume is going to be the integral as x goes from 0 to pi, because remember we're starting at x equals 0 over here on the left side, stacking all the way over to x equals pi. Those were also conveniently the bounds that they gave us, so we made sure we knew what this x-intercept was. And I have pi times my big radius squared, which is sine of x plus 2 squared, minus pi times my little radius squared, which is just 2 squared. And if you want to, you can simplify that down to be 4. That right there is our final answer for the volume for this guy. Let's go on to our last example for this one, which will be example 9. Now, we've actually seen this graph before. We found the area of this region when we did area between curves back in Learning Target 8A. Technically, that was the first part of a old free response problem. This is, I believe, part B of that same free response problem. So, let's read it. This was not calculator active, so we're going to have to figure out which graph is which, or which curve is which, but they did give us the graph. They say let R be the region in the first quadrant enclosed by the graphs of f of x, which is 8x cubed, and g of x, which is sine of pi x, as shown in the figure to the right. Well, 8x cubed is a cubic graph, so that's actually the bottom, since our cubic graph, remember, curves down and up and over, so I'm actually concave up in the first quadrant, so that graph down there is going to be f of x, which is the 8x cubed. The sine of x, remember we had in our last example, curves up and around and it would keep going, so that curve right there is going to be sine of x. Now, I'm going to label this in another portion of this so that I'm not intersecting what we're about to rotate by. So that curve right there is g of x, which is the sine. Now, they say write but do not evaluate an integral expression for the volume of the solid generated when R is rotated about the horizontal line y equals 1. Now, I want you guys to pause the video again and decide, is this a disk or a washer? Will we be in terms of x or in terms of y? And then also take the time to draw out either your radius or your radii that you get. Okay, let's start drawing on this graph then. So we're rotating about y equals 1. Well, y equals 1 is this horizontal line running through the graph up there, and I'm flipping this up and around. And I'm not going to draw the three-dimensional shape this time. This will flip up. You'll get a mirror image on the other side. But what I am paying attention to is the fact that there is this open space here, which tells me that I do have a washer. So So I will be finding 2 radii as we go through this. The other thing I'm paying attention to is because I'm going to slice perpendicular to the axis of revolution, it means that my radii are going to be going up and down. So if I draw my first radius, it's going to start at the axis of revolution and go down to the first curve, which is g of x. And then to get my second radii, it's going to start back at the axis of revolution and go all the way down to the second curve, which is actually f of x for this example. And now we can go ahead and try and figure out what our bounds are. Well, if I'm slicing up and down, then what that tells me is that I'm stacking side to side here. So I'm stacking this up like I would stack up a loaf of bread, and I'm starting at the left side over here, which is x equals 0, and it's going all the way along. They keep stacking up until they stop right here where the curve intersects, and that happens to be at x equals 1/2. That is a very messy 0. Let's clean that up. Okay, so my bounds then are going from x equals 0 all the way to x equals 1/2. The next thing I need to figure out is, well, what are my equation for my radii? So let's start with the big radius here. So the big radius is starting at the axis of revolution and going all the way down to the bottom curve since I passed the first curve. Now, because I'm in terms of x, I'm looking at top minus bottom. So the top curve here is actually y equals 1, minus the bottom curve here is this 8x cubed, but the problem labeled it as f of x, so I'm going to just call it f of x and save myself some time writing. I can do the same thing to find my little radius. So my little radius is starting at the axis of revolution and going down to this sine curve, which is g of x. So I'm also thinking top minus bottom. So the top curve there is 1 minus the bottom curve here is this sine curve, but they called it g of x. I might as well take that and use it to my advantage so I have less to write out. Now that I have my bounds and I have my radii, let's go ahead and set up what our final equation for volume will be. So volume of this guy, having lots of difficulties with the stylus tonight. The volume for this guy will be the integral as x goes from 0 to 1/2, since I was stacking up along the x-axis like a loaf of bread, of pi times my big radius, which will be 1 minus f of x, squared, minus pi times my little radius, which is 1 minus g of x squared, and I am with respect to x this time. So this whole piece right there, if I can box it, there we go, will be our final answer for our volume. And anytime the AP test or any test that you take, if they define functions for you, it is more than fair game to use those functions in your equations. There's no need to have to write out 8x cubed if you've labeled it as f of x, and there's no reason to write out sine of pi x if you've labeled it as g of x. Okay, this is the end of this portion of the video. The last part of Learning Target 8B is going to talk about, well, if instead of rotating regions about lines, what if I kind of build out a three-dimensional graph at you, like if you're building it out of the computer screen towards you. So we'll pick up with that in our next video.